take a breath. You're sitting somewhere right now, perhaps in a quiet room, or on a train moving through morning light, or curled into a corner of something familiar. Wherever you are, time is passing. You can feel it almost. A slow tick behind everything. The moment arriving, pausing just long enough to be noticed, and then dissolving into the next. Hello and welcome back to Infinite Science. It feels reliable. It feels like the ground beneath all other experience. And in most ways, for most of a human life, it is. The sun rises, the clock moves, you grow older. Time is the most intimate companion any of us will ever have. Closer than memory, more constant than breath. And space? Space simply is. The distance between you and the wall across the room. The stretch of road between your home and someone you love. The vast, silent gap between stars. Space feels like the container of everything. An absolute stage on which the performance of existence plays out. This is the world we are born into. This is the world our nervous systems are tuned to navigate. It is a world of fixed distances and steady clocks, of cause following effect, of here being different from there, and now being different from then. It is a world that makes intuitive sense, and it is, in a deep and strange and beautiful way, not quite real, not in the way we think it is. This isn't a warning, it isn't unsettling, or at least it doesn't have to be. It is, if anything, an invitation, because underneath the steady surface of everyday life, the universe holds a secret that Einstein quietly uncovered more than a century ago. A secret that physicists understand, that textbooks contain, that satellites depend on to function, and yet a secret that rarely makes it into ordinary conversation. Not the part about energy and mass, not the famous equation, something quieter than that, something that cuts closer to the bone. The secret is this: space and time are not separate things. They are not the fixed, independent backdrops we imagine them to be. They are woven together into a single, flexible, dynamic fabric. And that fabric can bend, stretch, curve, and ripple depending on where you are and how fast you're moving. More than that, what you experience as now, this precise, vivid, undeniable present moment, is not universal. It is not shared by everyone. It belongs to you in a way that is deeply personal and deeply physical. The universe does not have a single clock. It has many, and they do not agree. Let that settle for a moment. Don't push it away. Don't rush to make it make sense. Just let it be strange for a little while, the way a beautiful piece of music is strange before you understand it. Full of something, even before the meaning arrives. We're going to take our time with this. We're going to walk slowly through it, the way you'd walk through a cathedral, pausing, looking up, letting the scale of the thing reach you. But before we go to Einstein, before we go to bending light and curving space and the strange elasticity of time, we need to start here, with the ordinary, with the everyday illusion that feels so solid, so dependable, so completely obvious, because that's where the wonder lives. Not in the strange equations, not in the exotic extremes, but in the quiet gap between what we assume is true and what actually is. Think about your morning. You woke up. The clock said something, a number, a time. You may have ignored it or groaned at it or felt relieved by it. But somewhere in that first conscious moment, your brain oriented itself in time. It understood roughly where it was. Not just in space, not just in this bed, in this room, in this building, but in the flow of events. Behind you was yesterday. Ahead of you was today. And the present moment was a thin, moving line between them. This is so automatic, so deeply wired into human cognition, that it barely feels like an assumption. It feels like reality itself. Time has a direction. Time has a speed. And everyone, everywhere shares the same version of it. Your friend in another city is also in this morning. Someone on the other side of the planet is also living through this same Wednesday, this same October, this same year. Time is a river and we are all in it together, carried along at the same rate in the same direction. That's the assumption. And it's understandable, it's not foolish, for the scale of a human life, the distances we walk, the speeds we drive, the heights we climb. It's accurate enough, good enough to build civilizations on, good enough to schedule meetings and celebrate birthdays and measure the lives of generations. But it's an approximation, a useful, beautiful, comfortable approximation. And like all approximations, it breaks down when you push it to its limits. Consider for a moment how you know things. You know the chair is solid because you can sit in it. You know the floor is flat because you can walk on it without stumbling. You know the sun is bright because it hurts to look at directly. Your knowledge of the physical world comes almost entirely through your senses. And your senses evolved over hundreds of millions of years to navigate a very specific range of scales. Not too small, not too large, not too fast, not too massive. The middle ground, the human scale world. We are exquisitely calibrated for this range. Our eyes evolved to detect light in a narrow band of wavelengths. Our ears evolved to detect pressure waves in a narrow band of frequencies. Our bodies evolved to move at speeds that are, cosmically speaking, essentially zero. And our brains, and remarkable as they are, built their models of reality based on this narrow slice of experience. There is no reason, none at all, why the universe should be required to behave in ways that feel intuitive to creatures like us. The universe was not designed to be understood by nervous systems that evolved on a medium-sized planet. It was not organized for our convenience. And yet, and this is remarkable, we have been able to reach beyond our instinctive models. Through mathematics, through careful observation, through the willingness to follow logic wherever it leads, even when it leads somewhere uncomfortable. We have managed to understand things that no amount of ordinary experience could have revealed. Einstein was one of the people who led this reach, and he did it, at least partly, not through giant experiments or enormous machines, but through thought, through sitting quietly with the implications of what physics already knew, following the thread and letting it lead somewhere completely unexpected. Let's begin with something simple: light. In the late 1800s, scientists had a problem. Physics had been doing extremely well. Newton's laws described the motion of objects with extraordinary precision. Electromagnetism had been unified into elegant equations by James Clerk Maxwell. Everything seemed to be falling into place. But light was strange. Maxwell's equations predicted that light travels at a specific speed, approximately 300,000 kilometers per second. This was confirmed by experiment. The speed of light was real and measurable. The problem was, relative to what? When we say a train is moving at 100 kilometers per hour, we mean relative to the ground. When we say a sound wave travels through air at roughly 340 meters per second, we mean relative to the air. Speed in our everyday understanding always implies a reference point. So if light travels at 300,000 kilometers per second, what is it moving relative to? The intuitive answer at the time was some invisible medium that fills all of space. Something everything moves through. Scientists called it the luminiferous ether. The ether was supposed to be the absolute reference frame, the fixed backdrop against which everything else moved, including light. It was a perfectly reasonable idea. it was also wrong. In 1887, Albert Michelson and Edward Morley performed a brilliant experiment designed to detect the ether. The idea was simple. If Earth is moving through the ether as it orbits the Sun, then light traveling in the direction of Earth's motion should appear to move at a slightly different speed than light traveling perpendicular to it. For the same reason that walking into the wind feels different from walking with the wind. They measured again. They measured with extraordinary precision. The result was bewildering. The speed of light was the same in every direction. No matter how you oriented the measurement, no matter what time of year, no matter what direction Earth was moving, there was no ether, there was no absolute rest. There was just light moving at the same speed for everyone. This was not a small discrepancy. This was not a rounding error. This was a fundamental crack in the foundations of physics. For nearly 2 decades, the problem sat there, unsolved, like a splinter in the collective mind of physics. Various patches were proposed. Some worked mathematically, but not conceptually. The pieces didn't fit together cleanly. And then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, sat down and thought about it very carefully. His name was Albert Einstein. And he didn't try to patch the problem. He followed it all the way to where it led. Einstein's starting point was elegant in its simplicity. What if the speed of light is genuinely constant for all observers? Not as a strange accident, not as a coincidence, but as a fundamental law of nature, as deep and as real as anything physics had discovered. What if the speed of light is the one thing in the universe that truly does not change, depending on how you're moving? If you accept that, just that, and follow the logic with absolute rigor, something remarkable happens. Everything else has to change. If the speed of light is fixed, then the things we thought were fixed, space and distance, time and duration, cannot be. They have to be flexible, they have to adapt, to stretch and compress in exactly the right ways to keep the speed of light constant for every observer. This is the quiet revolution. This is the idea that changed everything. Not things move fast, not energy equals mass, though both of those come from it. The deep idea is this: space and time are not absolute. They are relative. They are personal. They depend on the observer. And once you accept that, the world is never quite the same again. Let's slow down and really feel what relative means here. Imagine you're on a train, a perfectly smooth, silent, perfectly fast train. The kind that glides so smoothly, you might almost forget you're moving. You're sitting at a table, and on the table is a coffee cup. From your perspective, the coffee cup is perfectly still. It's not moving at all. Now, imagine someone standing beside the tracks, watching the train go by. From their perspective, the coffee cup is moving at, let's say, 200 kilometers per hour. It is streaking past them in a blur. The coffee cup is both still and moving at 200 kilometers per hour. Both of these statements are true. They are just true from different perspectives, different frames of reference. This is not new. This goes all the way back to Galileo. There is no contradiction here. Motion is relative to the observer. Now here's where it gets interesting. On that same train, you point a flashlight forward in the direction of travel. The light shoots out ahead of you. From your perspective, it is moving away from you at the speed of light, 300,000 kilometers per second. Now, consider the person standing by the tracks. According to the old intuitive logic, the Newtonian logic, they should measure the light as moving slightly faster than the speed of light. After all, the light is moving at 300,000 kilometers per second relative to the train, and the Train is moving at 200 kilometers per hour relative to the ground. So relative to the ground, the light should be moving at 300,000 kilometers per second plus 200 kilometers per hour. That's how speeds add in the everyday world. That's how common sense says it should work. But it doesn't work that way for light. The person by the tracks measures the light at exactly 300,000 kilometers per second. Not a hair faster, not a hair slower. How is this possible? How can both people, moving at different speeds, measure the same beam of light at the same speed? The answer is because time is passing at different rates for them, because the distances they measure are different, because space and time are not fixed. They stretch and compress to ensure that every observer in every state of motion measures light at exactly the same speed. It sounds like a trick. It sounds like cheating, but it isn't. It's the deep structure of reality. And once Einstein understood this, once he followed this thread all the way to its conclusion, he realized that space and time are not two separate things. They are two faces of a single, unified thing. He called it spacetime. Spacetime. The word is simple. The concept is extraordinary. Think of space as you normally do, 3 dimensions, up and down, left and right, forward and backward. You can move through these 3 dimensions freely. You can choose to go left or right. You can choose to go up or down. These are your spatial dimensions and you navigate them with freedom. Now add time. A 4th dimension. Not a spatial one, but a temporal one. The dimension through which you move in one direction, always forward, always at what feels like a constant rate. In Einstein's framework, these 4 dimensions are not separate. They are woven together into a single 4-dimensional fabric, space-time. And everything that exists, every particle, every planet, every beam of light, exists not just in space and not just in time, but in space-time. Every event in the universe has a location in space-time, not just where, but when. And those two things cannot be separated. Here's an image that might help. Imagine a perfectly flat rubber sheet stretched tightly in all directions. This is space-time. Simplified, 2-dimensional, but it carries the essential quality. It's a fabric, it has extent, and things exist on it, within it, as part of it. Now take a heavy ball, say a bowling ball, and place it on the rubber sheet. The sheet bends, not around the ball, not under the ball. The sheet curves everywhere near the ball in a smooth, continuous depression. The ball sits at the bottom of a curved region in the fabric. This is gravity, not a force reaching out through empty space, not invisible fingers pulling on distant objects, but a curvature. A warping of the space-time fabric caused by the presence of mass. And other objects moving through that curved region of space-time don't get pulled. They simply follow the curves, the paths of least resistance through the warped geometry. Einstein called these paths geodesics. They are, in a precise mathematical sense, the straightest possible lines through curved space-time. When the Earth orbits the Sun, it is not being pulled by the Sun's gravity in the way a ball on a string is pulled. It is following a geodesic, the straightest possible path through the curved space-time created by the Sun's enormous mass. When a thrown ball follows a parabolic arc through the air, it is not being tugged downward by gravity. It is following a geodesic through the slight curvature of space-time near Earth's surface. Gravity is not a force. Gravity is geometry. Let that breathe. Gravity is geometry. What Newton described as a force, the invisible pull of mass on mass, acting at a distance, is, in Einstein's description, something entirely different. It is the shape of space and time themselves. It is the curvature of the fabric. This is not a minor revision. This is not an update to the instruction manual. This is a completely different way of understanding the structure of reality. In Newton's universe, space is a fixed three-dimensional stage and time is a universal clock ticking steadily in the background. Objects exist in space and move through it, affected by forces that act between them. In Einstein's universe, there is no fixed stage. There is no universal clock. There is a four-dimensional fabric, spacetime. And that fabric is dynamic. It curves, it ripples, it responds to everything that exists within it. And the way objects move is not determined by forces, but by the shape of the fabric. The Earth doesn't orbit the Sun because the Sun is pulling it. The Earth orbits the Sun because the Sun has bent space-time into a shape in which the Earth's natural geodesic path is a near circle. It's the difference between a marble pulled toward a magnet and a marble rolling along the inside of a bowl. The forces in the first case come from outside. The curve in the second case comes from the shape itself. In Einstein's universe, everything is the bowl. Now here is where the story starts to turn toward the secret, the thing that is rarely discussed, the implication that sits quietly at the heart of all this, waiting to be noticed. If space-time is a single fabric, if space and time are woven together, then bending space-time doesn't just affect space, it affects time too. Mass doesn't just curve space, mass curves time. Near a massive object, a planet, a star, a black hole, time itself flows more slowly. Not metaphorically, not as an analogy, actually measurably, verifiably slowly. This is called gravitational time dilation, and it is one of the most mind-expanding and least discussed consequences of Einstein's theory. Here is a way to feel it. Imagine two identical, perfectly synchronized atomic clocks. Clocks so precise they lose less than a second over millions of years. You take one clock to the top of a very tall mountain. You leave the other at sea level. You let them run for a year. Then you bring them back together and compare. They do not agree. The clock at the top of the mountain, farther from Earth's gravitational center, sitting in slightly less curved space-time, has ticked slightly faster. It has recorded slightly more time. The clock at sea level, deeper in Earth's gravitational well, has ticked slightly slower. The difference is tiny by human standards, on the order of microseconds over a year. But it is real, it has been measured. It is not a theoretical prediction waiting to be confirmed. It is an observed, replicated, experimentally established fact. And it has practical consequences. The GPS satellites orbiting Earth are far enough from Earth's surface that they sit in slightly less curved space-time than we do. This means their clocks tick faster than clocks on the ground. If this effect were not accounted for, if the GPS system did not correct for it, the satellite's position calculations would drift by kilometers every day. Every time a GPS system gives you accurate directions, it is applying Einstein's general relativity. It is correcting for the fact that time flows at a different rate in orbit than it does on the surface. Einstein's space-time curvature is not a philosophical abstraction. It is built into the infrastructure of modern navigation. But gravitational time dilation is only half the story. The other half comes from the special theory of relativity, the part that came first in 1905. And it says something equally strange. Motion also affects time. The faster you move through space, the slower you move through time. Or, to say it more precisely, the faster your relative motion, the more slowly time passes for you from the perspective of a stationary observer. This is called velocity-based time dilation, and it is just as real, just as measurable, and just as deeply built into the structure of reality. Here is the classic image. Imagine a clock made of light. Two mirrors facing each other, with a beam of light bouncing back and forth between them. Every round trip of the light is one tick of this clock. It's elegant, perfectly regular, and easy to reason about. Now put this clock on a spaceship moving at a significant fraction of the speed of light. From your perspective, standing still and watching the spaceship pass, you see the light beam in the clock not bouncing straight up and down, but tracing a diagonal path. Because the clock is moving sideways while the light is bouncing up and down, the light has to travel a longer path between reflections. But the speed of light is constant. If the light is traveling a longer path at the same speed, it takes longer to complete each tick. From your stationary perspective, the moving clock is ticking more slowly. Aboard the spaceship, everything seems normal. The clock ticks at what feels like a regular rate. Time feels ordinary. But relative to you, relative to the rest of the universe watching the ship pass, that clock is running slow. Time itself aboard the moving ship is dilated, stretched by the motion. This is not science fiction. This is not a thought experiment that remains hypothetical. In 1971, physicists Joseph Haffel and Richard Keating flew 4 atomic clocks around the world on commercial airplanes, and then compared them to atomic clocks that had remained stationary on the ground. The clocks on the planes had ticked at different rates, accounting for both the velocity time dilation, moving clocks run slow, and the gravitational time dilation, clocks at higher altitude run fast. The predictions of general and special relativity were confirmed to within the precision of the experiment. Particle physics confirms this too. Certain particles called muons are created in the upper atmosphere when cosmic rays collide with air molecules. Muons are unstable. They decay very rapidly with a half-life of about 2.2 microseconds. At the speeds they're moving by all rights, they shouldn't survive long enough to reach Earth's surface before decaying. But they do. They reach the surface in large numbers. How? Because from the muon's perspective, the journey is shorter. Distances contract at relativistic speeds, and from our perspective, the muon's internal clock is running slowly. It hasn't experienced enough time to decay before reaching us. Both descriptions are correct. Both are real. Time dilation is not an illusion. It is physically real, and it explains why we detect muons at all. The universe is not obligated to match our intuitions, but it is extraordinarily precise and extraordinarily willing to be measured. Now we come to the heart of it, the part that is rarely talked about, the part that, even among people who know about time dilation, even among people who understand that time runs slower in strong gravity and at high speed, is often not fully felt. Not just understood in passing, felt, absorbed, let in. There is no universal now. Let that settle. Right now, at this precise moment as you read or listen to these words, there is no single now that all of reality shares. The moment you are experiencing is not a moment that belongs to the universe. It belongs to you in a way that is precise, physical, and personal. This is not poetry. This is not metaphor. This is the formal consequence of Einstein's special relativity, and it has a name. It is called the relativity of simultaneity. Here is a thought experiment, one of Einstein's favorites. Imagine a train, long, fast, and perfectly straight. At the exact center of the train, there is a light source. When triggered, it sends light in both directions simultaneously. Toward the front of the train and toward the back. From inside the train, the light reaches both ends at the same time. The front and back of the train are equidistant from the center. The light travels at the same speed in both directions. so both ends are illuminated simultaneously. Now, consider someone watching from beside the tracks as the train passes. They see the same light pulse, but from their perspective, the train is moving. While the light is traveling, the back of the train is moving toward the source, and the front of the train is moving away from it. This means the light has a shorter distance to travel to reach the back, and a longer distance to travel to reach the front. Since light travels at the same speed in all directions, same speed for everyone, the light reaches the back of the train before it reaches the front. The two events, light reaching the front, light reaching the back, happens simultaneously for the person on the train. The same two events do not happen simultaneously for the person on the ground. There is no contradiction, there is no error. Both observers are measuring correctly, using perfect instruments following all the laws of physics, and they disagree about whether two events happened at the same time. Simultaneity is relative. There is no absolute answer to the question, did these two things happen at the same time? The answer depends on your state of motion. This sounds technical. Let's feel it at a larger scale. You are looking at a star. It's a beautiful night, and the sky is clear, and you find one star in particular that catches your attention. You watch it for a moment. It's there, it's real, it's glowing. But here is the thing. You are not seeing the star as it is. You are seeing the star as it was. You are looking into the past. Light from that star takes years, sometimes thousands of years, to reach your eyes. If the star is 1,000 light years away, the light you are seeing right now left that star 1,000 years ago. What the star is doing right now, whether it's still shining, whether it has exploded, whether it has been swallowed by something, you cannot know. That information has not yet reached you, but it's stranger than just you're seeing the past. The question, what is that star doing right now? What does right now even mean across 1,000 light years? In Newtonian physics, this question has a clean answer. There is a universal present moment, and the star is either shining or not in that moment, regardless of when the information reaches you. In Einsteinian physics, the question is not well defined. Different observers, people moving at different speeds or in different gravitational fields, will disagree about what event at your star is simultaneous with this moment on Earth. Not because their clocks are wrong, not because their measurements are imprecise, but because simultaneity itself is not absolute. It is relative to the observer. What now means at a distance depends on who is asking. There is a concept in physics called the block universe, or more formally, eternalism. It's a philosophical interpretation of space-time that arises quite naturally from taking Einstein's ideas seriously. The idea is this: if different observers have different nows, if simultaneity is relative, if the past and the future are just as real as the present in the mathematical structure of space-time, then perhaps the past and the future are not gone and not yet arrived. Perhaps they simply exist in a different region of space-time, just as real as the present moment. In this view, space-time is not a stage on which events happen. Space-time is a structure in which events simply are. The Big Bang is not in the past. It is at one end of space-time. The far future is not yet to come. It is at the other end. Every event that has ever occurred or will ever occur is already embedded in the four-dimensional structure, the way all the pages of a book are part of the book, even if you're only reading one page at a time. You experience time as a flow, a movement through this structure, because you are a physical system moving through space-time. The you of 5 minutes ago and the you of 5 minutes from now are different slices through a four-dimensional object that is, in some sense, just there. This is called the block universe because in this view, space-time is like a block. Static, complete, the entirety of existence laid out at once in a four-dimensional structure that has no privileged now. Does this mean the future is determined? Does this mean free will is an illusion? These are questions that physics, honestly, cannot fully answer. The block universe is an interpretation, a way of understanding what the equations mean. It is taken seriously by many physicists and philosophers. It is not universally accepted, but it arises almost naturally from taking the relativity of simultaneity seriously. If there is no universal now, if different observers have genuinely different presents, then the ordinary idea of the present as the only real moment starts to look less like physics and more like a feature of human consciousness. The universe, it seems, does not share our sense of the present. Let's dwell here for a moment. You are sitting somewhere reading or listening. The present moment feels undeniably real. It feels like the only thing that is real. The past is gone, a memory, a trace. The future hasn't arrived, a possibility, a hope, or a fear. Only this, right now, is actual. That feeling is real. It is an accurate description of your experience. But what physics suggests, and what the mathematics of space-time implies, is that this feeling of now being uniquely real is a feature of your position and motion in space-time. Another observer, moving differently, has an equally valid now that is different from yours. Neither is more correct than the other. The universe does not have a single privileged moment called now. It has many, depending on who is asking and how they are moving. And across cosmic distances, the disagreement becomes enormous. What an observer moving at a significant fraction of the speed of light, 1 billion light-years away, would consider simultaneous with your current moment. The event in our cosmic neighborhood that they would say is happening right now, along with your reading of this sentence, could be an event that, from our perspective, occurred millions of years ago, or millions of years in the future, depending on the observer's motion. This is not a paradox. It does not break physics. There are rules, consistent, mathematical, experimentally verified rules, that govern how different observers' versions of now relate to each other. The universe is not chaotic or arbitrary, but it is deeply, profoundly, beautifully strange. And the strangeness is not a sign that something is wrong. The strangeness is a sign that reality is far richer, far more intricate than our everyday experience can reveal. Our everyday experience is of a small world, a human-scaled world, a world where we move at speeds that are, relative to light, essentially zero, where the gravitational differences we encounter are tiny, where the effects of relativity are so small that they are utterly invisible to unaided experience. We evolved in this world, our intuitions are tuned to this world, and our intuitions are excellent for this world. They let us catch falling objects, navigate terrain, build shelter, predict seasons. They are exquisite tools for the scale at which life happens. But they are not descriptions of the deep structure of reality. The deep structure of reality is space-time, dynamic, flexible, relational, observer-dependent. And once you glimpse it, really glimpse it, not just understand the words but feel the implications, the world becomes a stranger and more beautiful place. Let's go deeper into time. Let's really sit with what it is and what Einstein's framework does to our understanding of it. In everyday life, time is experienced as a flow. It has a direction. It moves from past to future, from earlier to later, from cause to effect. This direction feels absolute. You cannot unremember a memory by deciding to. You cannot unbreak a dropped glass. The past is fixed, and the future is open, and the present is the thin boundary between them. This is such a fundamental feature of experience that it is almost impossible to imagine otherwise. And yet, the fundamental equations of physics, including Einstein's equations, including quantum mechanics, are almost entirely time-symmetric. They work equally well in both directions of time. A movie of two particles interacting played backwards is, at the level of the equations, just as valid as the forward version. The directionality of time, the arrow of time, is not written into the basic laws in the obvious way we might expect. It emerges, most physicists believe, from the statistical behavior of large numbers of particles and from the extraordinarily low entropy state of the early universe. But that's a deep rabbit hole, and let's not fall entirely into it. For our purposes, the key insight is this. Einstein showed that time is not what common sense says it is. Time is not constant. It flows at different rates in different conditions. Time is not independent of space. It is woven together with it. Time is not universal. Different observers have different nows. And perhaps most profoundly, the past, present, and future may all be equally real, laid out in the structure of space-time like different regions of a landscape. Each one as actual, as physical as any other. Here's an image that might help make time dilation feel real rather than abstract. Imagine you have a certain budget of space-time motion. You are always moving through space-time. Always. Even when you are sitting completely still in space, you are moving through time. The two components of your motion, through space and through time, are always there and they are connected. Here's the connection. Every object in space-time moves at the same speed through space-time overall. The speed of light is the universal speed limit, but it is also, in a precise sense, the speed at which everything moves through space-time. When you are sitting still in space, all of your space-time motion is going into moving through time. You experience time at its maximum rate. When you start moving through space, some of your space-time motion is redirected from time into space. You are trading time motion for space motion, and as a result, you move through time more slowly. The faster you move through space, the more of your space-time motion is taken up by spatial movement, and the less is left over for temporal movement. Time for you slows down. At the speed of light, if you could reach it, which massive objects cannot, all of your space-time motion would be in the spatial direction. None would be left for time. Time, for you, would stop entirely. A photon, particle of light, does not experience time. It exists in an eternal present from the moment it is emitted to the moment it is absorbed. For light, there is no journey. There is no duration, there is only emission and absorption with nothing between. This is why black holes are so extraordinary. A black hole is a region of space-time where the curvature has become so extreme, caused by such an enormous concentration of mass, that the geometry itself has changed in a fundamental way. Near a black hole, time slows dramatically compared to time far away. Near the event horizon, the boundary beyond which nothing can escape, time slows to a crawl from an outside observer's perspective. If you could somehow watch a person falling toward a black hole from a safe distance, you would see something extraordinary. As they approach the event horizon, you would see them slow. Their movements would become slower and slower. The light from them would redshift, shift toward longer wavelengths as the photons climbed out of the gravitational well and lost energy doing so. From your perspective, They would approach the event horizon but never quite reach it. Time, for them, appears to nearly stop. From their perspective, however, if they were falling freely, in freefall, not fighting the gravity, they might not notice anything unusual as they crossed the horizon. They would fall through, into the interior. The strangeness would come later. Two perspectives, two descriptions of the same event, both valid, both consistent, neither more correct than the other. This is the nature of space-time. It is not one thing seen from all angles. It is many descriptions, each anchored to a particular perspective, each equally valid, each capturing something real that the others cannot quite capture in the same way. Let's take a moment to consider what this says about the nature of experience. You have a perspective, a particular location in space, a particular speed relative to other things, a particular depth in the gravitational well of the objects around you. These are not just facts about your circumstances. They are facts about your time, about how quickly the moments are passing, relative to others in other circumstances. The person at the top of a skyscraper is aging, very slightly, faster than the person in the basement. Both are living their lives with no sense of difference. Both feel time passing normally, but objectively, physically, measurably. They are in different temporal streams. Over a human lifetime, the difference between a person who lives at high altitude and a person who lives at sea level amounts to a few microseconds. Invisible, unmeasurable by any human sense. But the principle is the same one that makes GPS satellites require correction. The same one that makes black holes bend time so severely that an observer near the horizon ages incomparably more slowly than one far away. It is not a different effect at different scales. It is the same effect. Reality's geometry, doing what it does, everywhere, all the time. There's something both humbling and strangely personal about all this. Your lifetime, the entire span of your existence from birth to death, is a trajectory through space-time. Not just through space, not just through time, through the unified fabric of both. Every choice that leads you to a different place leads you through a slightly different space-time path. Every mountain you climb, every flight you take, every moment of acceleration or deceleration, all of these are, in the tiniest measurable ways, affecting the rate at which time passes for you. None of this is detectable by your senses. None of it will ever meaningfully change your life in practical terms. You will live your decades and they will feel like decades, regardless of whether your path through space-time has taken you slightly higher or slightly faster than someone else's. But underneath the lived experience, something extraordinary is happening. You are a physical object moving through a curved four-dimensional fabric. You have your own proper time, the time measured along your specific space-time path. And that proper time is yours, uniquely, in a way that no other object in the universe fully shares. Not because you are special, but because you are physical, because you exist with a specific mass and motion and location, because you are part of space-time, not just in it. Zoom out. Let's leave the human scale entirely for a moment and try to see space-time from a genuinely cosmic perspective, or as close to one as we can manage. Our solar system is, from a cosmic standpoint, a relatively simple place. One medium-sized star, 8 planets, a scattering of moons and asteroids and comets. The sun's gravity curves space-time throughout the solar system, and each planet traces its geodesic, its path through that curved geometry, in its own quiet way. The effect on time within our solar system is small, but real. Deeper in the sun's gravitational well, closer to the sun's surface, space-time is more curved and time flows more slowly. Mercury, the innermost planet, sits in a slightly stronger gravitational field than Neptune. Mercury's year is shorter in another sense too. Its orbit precesses. Its ellipse rotates slowly over time. And the precise rate of that precession could not be explained by Newtonian gravity. It was a long-standing mystery. Einstein's general relativity explained it exactly, without adjustment, in 1915. The small extra curvature of space-time near the Sun produced precisely the precession of Mercury's orbit that astronomers had been observing for decades without explanation. It was, for Einstein himself, one of the most thrilling moments of his scientific life. The numbers worked. The universe confirmed the theory at a precision that Newton's physics could not match. Move further out. Imagine leaving the solar system, drifting away from the Sun on a long, slow arc. The Sun shrinks behind you. Its gravitational influence weakens. Space-time locally becomes flatter, less curved. Time relative to someone sitting on Earth's surface begins to flow just slightly faster. You travel for years, decades. The Sun becomes a bright star, then just a star, then a point of light indistinguishable from its neighbors. You are in the space between stars. This space is not empty. It is not nothing. It is full of space-time. The fabric itself, mostly flat here, away from massive objects but still continuous, still real, still the medium through which everything moves. After years of travel, you approach another star. Perhaps Alpha Centauri, our nearest stellar neighbor, roughly 4.2 light-years from the Sun. As you draw closer, space-time curves around you again. The star's gravity creates a gravitational well, and you are descending into it. If Alpha Centauri had planets, the innermost would be in slightly more curved space-time than the outer ones. Time would flow more slowly for them. Not dramatically. These are modest differences as stars go, but real. Now think of what happens near a more massive object. Neutron stars. These are the collapsed cores of massive stars that have ended their lives in supernova explosions. A neutron star packs roughly 1 to 2 times the mass of the Sun into a sphere only about 20 kilometers across. The density is almost incomprehensible. A tablespoon of neutron star material would weigh as much as a mountain. The space-time near a neutron star is dramatically curved. Gravity at the surface is roughly 200 billion times stronger than gravity at Earth's surface. Time near a neutron star surface runs measurably, significantly slower than time far away. If you could somehow stand on the surface of a neutron star, ignoring for a moment that you would be instantly crushed to a film thinner than an atom, and observe a clock far away in space, that clock would appear to run at a much faster rate than your own. The universe out there in flat space-time would seem to be running in fast forward from your perspective on the surface. And from the perspective of someone far away watching you, assuming they could somehow see you, you would appear to be moving in slow motion. Not just your body, everything. Your thoughts, your processes, your biological rhythms, all slower relative to them because time itself is slower where you are. But neutron stars are not the extreme. Black holes are. A stellar black hole forms when a neutron star is massive enough to continue collapsing. Past the neutron star stage, past any known form of resistance, into a singularity. A region of space-time where the curvature is, mathematically, infinite. Where our equations break down and stop giving meaningful answers. The event horizon, the boundary of no return, is not a physical surface. There is no wall there, no membrane, no obvious boundary to cross. It is simply the radius from which the escape velocity equals the speed of light. Beyond it, not even light can escape. The gravitational time dilation near the event horizon is extraordinary. To a distant observer, someone falling toward the event horizon appears to slow dramatically, their light red shifting as they approach. They appear to freeze there, infinitely slow, never quite crossing, because from outside, the time at the horizon is infinitely dilated. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the dark region at the center of the luminous ring of superheated gas orbiting the black hole in galaxy M87, some 55 million light-years away. That image, that remarkable, blurry, historic photograph, was a direct observation of the region where space-time curvature becomes so extreme that light is bent into a ring and the interior becomes unreachable. More recently, the same collaboration imaged Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. 4 million times the mass of our Sun, lurking in the galactic center, 26,000 light-years from Earth. We live in a galaxy that orbits around a black hole. Think about that scale for a moment. 26,000 light-years. The light reaching your eyes from the center of our galaxy left before humans had begun to develop agriculture, before the last ice age ended, before our ancestors had built the first permanent settlements. And at the center of all that, curving space-time with the mass of 4 million suns, is a black hole. The stars in our galaxy are not simply distributed randomly in space. They orbit. The entire galaxy rotates slowly around its center. Our Sun takes roughly 225 million years to complete one orbit of the galactic center, a period sometimes called a galactic year or a cosmic year. Earth has existed for about 20 galactic years. The universe has existed for about 60 galactic years, give or take. At the center of our galaxy, near Sagittarius A star, space-time is dramatically curved. Time flows more slowly there, relative to the quiet neighborhood where our Sun orbits. The stars in the innermost region of the galaxy, orbiting closely around the black hole, are in more curved space-time than we are. Their years, their centuries, their eons are slightly shorter in objective duration than ours. None of this is detectable to any life that might exist on planets around those stars. If any such planets exist, which seems unlikely given the extreme radiation environment near a galactic center, but the physics is the same. Gravity curves space-time. Curved space-time dilates time. The effect scales with the depth of the gravitational well. Zoom out still further. Our galaxy is not alone. It is one of at least 2 trillion galaxies in the observable universe. 2 trillion, the estimated count from deep observations by the Hubble Space Telescope and, now, with extraordinary precision, by the James Webb Space Telescope. Each galaxy is itself a vast structure of stars, gas, dust, and dark matter, held together by gravity, each with its own internal dynamics, its own space-time curvature, its own history of formation and evolution. The observable universe, the region from which light has had time to reach us in the 13.8 billion years since the Big Bang, is approximately 93 billion light-years in diameter. It is not the whole universe. It is just the part we can see. The total universe may be far larger, perhaps infinitely larger, depending on which cosmological model you favor. And through all of this, through every star, every galaxy, every vast filament of galactic clusters separated by emptiness so profound that our minds can only gesture at it, space-time extends, dynamic, responsive, woven through everything. The Big Bang itself was not an explosion in space. It was an expansion of space-time. Space itself grew rapidly, dramatically, almost inconceivably fast. In the first fractions of a second after the universe began, the galaxies we see rushing away from us are not moving through space. The space between them is expanding. The fabric is stretching. Space-time is not the container of the universe. It is the universe in a deep sense. The matter and energy within it are disturbances in the fabric, wrinkles, excitations, waves in a medium that itself has no edges, no boundaries, no center. There is a remarkable implication of all this expansion. There are galaxies far enough from us that the expansion of space between us and them is carrying them away from us faster than the speed of light. Not because they are moving faster than light through space. That is impossible. But because space itself is expanding, and across vast enough distances, the expansion rate exceeds light speed. This means there are galaxies we will never see, never reach. Their light, no matter how long we wait, will never close the gap. They are beyond our cosmic horizon, forever outside the observable. And those galaxies have their own cosmic horizons, their own observable universes, regions of space-time that are accessible to them, and to them only. The universe is not a single thing seen from all perspectives. It is many overlapping perspectives, each anchored to a particular location, each seeing a particular slice of what exists. This is the cosmic version of the same principle we met earlier at the human scale. Reality is relational. It depends on perspective. What you can access, what is real to you in the most operational sense, what light has reached you, what events have influenced you, is determined by your location in space-time. The universe is, in a very precise physical sense, different for everyone. There is one more dimension of the space-time story that we should not skip past. It begins with an observation that, when it was first made, was so surprising that even Einstein initially refused to believe it. The universe is expanding. Not in the sense that galaxies are flying through space away from a central point, but in the sense that space itself is growing. The fabric of space-time on the largest scales is stretching. And as it stretches, the galaxies embedded within it move apart from each other. Not because they are moving through space, but because the space between them is increasing. This was first observed by Edwin Hubble in the late 1920s, using the then new 100-inch telescope at Mount Wilson Observatory in California. He measured the distances to a number of galaxies, then called nebulae, and measured how fast they appeared to be moving away from us based on the redshift of their light. What he found was remarkable. The farther away a galaxy was, the faster it appeared to be receding. This was not a random scatter. It was a systematic relationship. Distance and recession velocity were proportional. This is exactly what you would expect if space itself were expanding uniformly. Every galaxy moving away from every other galaxy, with the rate proportional to the distance between them, because more space is being created between more widely separated galaxies. Hubble's discovery of the expanding universe was one of the great turning points in the history of astronomy. Einstein's general relativity had, in fact, predicted an expanding universe. Or rather, it had allowed for one. The field equations, when solved for a uniform distribution of matter on the largest scales, naturally produce solutions that are not static. They are either expanding or contracting. A perfectly static universe, it turned out, was actually unstable in the context of general relativity, like a pencil balanced on its tip. But Einstein had been so convinced that the universe must be static that he had introduced an extra term into his equations, a cosmological constant, specifically to cancel out the expansion and produce a static solution. He later called this his greatest mistake. Because when Hubble's observations confirmed the expansion, Einstein's original equations, without the cosmological constant, were vindicated. The universe is dynamic at the largest scale. It is not a static collection of galaxies sitting in fixed positions. It is an expanding fabric, carrying the galaxies along with it. And if the universe is expanding, if galaxies are moving apart from each other, then, running the clock backward, they must have once been closer together. Closer and closer, denser and denser, hotter and hotter, until you reach a beginning, a moment of extreme density and temperature from which the expansion began. The Big Bang. Not an explosion in space, but an event in which space itself was extremely compressed, and then began to expand. The expansion has been going on for approximately 13.8 billion years. It continues today. Here is something that can be difficult to truly absorb. When we look at the most distant galaxies, the ones at the edge of our observable universe, whose light has been traveling toward us for almost the entire age of the universe, we are not just looking far away in space. We are looking far back in time. The light from those distant galaxies left them when the universe was very young, in some cases only a few 100 million years after the Big Bang, a small fraction of the universe's current age of 13.8 billion years. The galaxies we are seeing were infant galaxies, recently formed, in a universe that was far denser and hotter than it is today. When the James Webb Space Telescope looks deep into the early universe and shows us galaxies that formed when the universe was only a few 100 million years old, it is doing something extraordinary. It is showing us the past, not a representation of the past, not a reconstruction, but the actual light from those early times, preserved and traveling through expanding space until finally arriving at our detectors. The universe has kept its own record. The cosmic microwave background radiation, the faint glow of microwave radiation that fills the entire sky, is the afterglow of the Big Bang itself. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for neutral hydrogen to form, and the universe became transparent to light for the first time. That light has been traveling ever since, and it is what we detect as the cosmic microwave background. When you look at the CMB, even in a conceptual, mind's eye way, you are looking at the surface of last scattering, the boundary in time between the opaque early universe and the transparent later universe. You are seeing 13.8 billion years into the past. The entire observable universe at that moment fits within your field of view. The whole thing, wrapped around us like a sphere of ancient light. Now here is something stranger still. The expansion of the universe is not slowing down, it's speeding up. This was discovered in 1998 by two teams of astronomers studying a particular type of supernova, Type 1a supernova, that can be used as precise distance indicators. They expected that the expansion should be slowing down over time due to the gravitational pull of all the matter in the universe on itself. Instead, they found that distant supernovae were farther away than expected, indicating that the expansion was actually accelerating. The universe is expanding faster and faster. This was so surprising, so contrary to expectations, that the discovery won its discoverers, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. What is causing the acceleration? We don't know. Whatever it is, we call it dark energy. It is the name for our ignorance, a placeholder for a physical cause that we have identified by its effects, but not by its nature. Dark energy appears to be a property of space itself. Empty space has some intrinsic energy. some kind of energy density that drives the acceleration. It might be Einstein's cosmological constant, rehabilitated. It might be something else entirely. Current observations are consistent with it being a constant, the same everywhere, at all times. But they cannot rule out that it varies. About 68% of the total energy content of the universe is dark energy. About 27% is dark matter, the invisible, non-light-emitting form of matter that makes up most of the mass of galaxies and galaxy clusters. Only about 5% is ordinary matter, the atoms, molecules, stars, planets, and every other thing we can see and touch and build with. The universe we can see and measure is a small fraction of the universe that exists. This is humbling, in a very specific way. We do not know what 95% of the universe is made of. We have excellent mathematical descriptions of what dark matter and dark energy do, how they affect the motion of galaxies, the structure of the cosmic web, the rate of expansion. But we do not know what they are, not in the deep, satisfying sense of knowing what atoms are made of or what light is. Dark matter does not interact with light. It does not emit it, absorb it, or reflect it. It interacts with ordinary matter only through gravity. We detect it by its gravitational effects. The extra mass needed to explain how galaxies rotate, the lensing effects that reveal more mass than the visible matter can account for. What it actually is, whether it is a new kind of particle not in our current standard model of physics, or something more exotic, or even something that requires new physics beyond the particle concept entirely, remains one of the great open questions. Dark energy is even more mysterious. It is not concentrated in galaxies or clusters. It is everywhere, uniformly distributed through space, apparently growing as space expands. It is, in a sense, the energy of nothing. The energy of empty space-time itself. If you had told Einstein in 1915 that nearly a century later, astronomers would discover that 68% of the universe's energy content was an invisible, homogeneous property of space itself, driving an accelerating expansion, would he have believed it? Probably not initially, but he might have smiled. The universe, after all, had already surprised him with gravitational waves and quantum mechanics and time dilation, and a dozen other things his equations predicted, but his intuition resisted. The universe is not obligated to be simple, but it is, always and reliably, precise. Let's step back from the physics for a moment, not to leave it, it will stay with us, but to ask what it means. What it suggests. Not in the abstract academic way, but in the quiet, personal, human way. What does it mean that time is relative? What does it mean that there is no universal now? What does it mean that the past and future may be as real as the present? Laid out in the structure of space-time, always there, always part of a larger whole that our limited perspective can only access one moment at a time? These are not questions with clean answers. They are questions that hover, that sit with you, that sometimes, in quiet moments, return uninvited and simply ask to be noticed. One thing this suggests gently is the contingency of our perspective. We feel as if our perspective is simply reality. That what we see, and the rate at which we see it, and the sequence in which events arrive, is just the way things are. But what physics tells us is that all of this is personal. It is attached to us, to our specific location and motion and gravitational situation. From another perspective, from a creature moving at a significant fraction of the speed of light, or existing near a massive object, the sequence of events in our lives might appear different. Cause and effect would be preserved. The laws of physics protect that, always. But the specific timing, the specific when of things would not be what we experience. Our now is ours. It is not shared, not universally anyway. There's something both isolating and beautiful in that. Each of us is, in a precise physical sense, alone in our present moment. Not emotionally alone and not cut off from other people, but cosmically alone in the specific experience of now. Separated from every other observer by the personal nature of our space-time path. And yet we share so much in practice. We share the Earth. We share a gravitational field and a rough range of velocities. We share enough of the same space-time neighborhood that our nows are nearly identical. Differ by nanoseconds or less, amounts invisible to experience. Our shared world is possible because the differences are so small at our scale. It is only when we step back and consider the cosmos that the fundamental individuality of now becomes apparent. There is a philosophical tradition, one that predates Einstein by centuries, that has asked whether time is real. Whether it is a feature of the external world, or a feature of consciousness, or some combination of both. Immanuel Kant, writing in the 18th century, argued that space and time are not properties of the external world at all. They are the form of our intuition, the structure of the lens through which our minds perceive experience. On this view, time is something we bring to experience rather than something we find in the world. This is an interesting idea and a philosophically sophisticated one. Though it is not what Einstein was saying. Einstein was not saying time is an illusion or a mental construct. He was saying something more precise, that time is real, that it is measurable, that it has definite physical effects, but that it is relative to the observer, not absolute. But perhaps there is a conversation to be had between Kant's intuition and Einstein's physics. Perhaps the extreme intimacy of now, the way it belongs, so specifically to each observer, the way it cannot be fully shared, suggests something about the relationship between consciousness and time that we have not yet fully understood. We do not know what consciousness is. We do not know, in the deepest sense, why there is experience at all, why there is something it is like to be a physical system rather than everything just happening in the dark. This is the hard problem of consciousness, and it is, in a real sense, unsolved. But we do know that consciousness is a physical process. It occurs in brains, physical systems moving through space-time, and those brains have their own proper time, their own temporal perspective, their own now. Perhaps the vividness of the present moment, the way now feels so undeniably real, more real than memory or anticipation, is a reflection, not of physics, but of what it is to be a particular kind of physical system. A system that processes information about its past and future in real time, that updates its model of the world on the fly, that is always here, always now, because it is always in the act of experiencing. This is speculation, but it is informed speculation, and it is the kind of speculation that seems invited by sitting quietly with the physics and asking not just, what does this mean mathematically, but what does this mean for us as the kinds of beings we are? Another thing the physics invites us to consider, the nature of change. We experience the world as changing. Things move, relationships shift, seasons turn, people age and are born and die. Change is so fundamental to experience that it is difficult to imagine a world without it. But in the block universe view, in the view suggested by taking space-time seriously as a four-dimensional structure, is there really change in a cosmic sense? Or is there just the structure of space-time with different configurations at different positions along the time axis? In a block universe, nothing changes in the sense of something that existed one way and now exists another way. Instead, there is simply the block, the whole structure, and different cross-sections of it are different. The difference between before and after is the difference between two different positions along the time dimension, both of which exist simultaneously in the block. This sounds like it might make change meaningless, or make time itself illusory, but this is not necessarily the conclusion. There is a difference between time being an emergent feature of a static structure and time being unreal. The warmth you feel is real, even if it is an emergent feature of the motion of molecules. The color red is real, even if it is an emergent feature of light hitting photoreceptors. The things that emerge from physical processes are not thereby unreal. They are just differently real than we might have naively expected. Similarly, if the flow of time, the felt sense of moments arriving and passing, is an emergent feature of physical systems moving through a four-dimensional structure that does not make it unreal, it makes it a genuine physical phenomenon, one that arises from the nature of what we are and how we are embedded in space-time. The present moment is real, change is real, the arrow of time is real. But they are real in a stranger, more complex, more beautiful way than our naive intuitions suggest. There's one more reflection worth sitting with. Einstein himself was deeply moved by these implications. He was not a man who separated physics from philosophy or science from human meaning. He wrote often about the emotional weight of the ideas he had uncovered. When his lifelong friend Michel Besso died in 1955, Einstein wrote a letter of condolence to Besso's family. He wrote that Besso has departed from this strange world a little ahead of me. That means nothing. For us convinced physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. This was not a cold or clinical statement. It was a gesture of comfort, shaped by Einstein's deep conviction that the block universe view, the view in which the past is not gone but only in a different region of space-time, meant something for how we think about those who have died. Whether you find that comforting or not is a deeply personal matter. There is no official scientific position on what the block universe implies for human grief or hope, or the question of whether the people we have lost are, in some sense, still there, in a region of space-time we can no longer reach, but which exists just as surely as tomorrow. But it is worth knowing that the man who discovered all of this was not indifferent to its human implications. He saw, in the strange geometry of space-time, something that spoke to questions that have always been at the heart of human life. What does it mean to live with this knowledge? Not for scientists only, for anyone. For you now, here, reading or listening in whatever small or large space you currently inhabit. What changes, practically, if you absorb the idea that your now is yours alone, that the past and future are real, that the universe does not share your temporal perspective, that space and time are a single dynamic fabric that curves around every object in existence? Probably not much in terms of your daily choices. You will still make breakfast and answer messages and navigate traffic and tend to the relationships that make your life feel like a life. The practical world operates at the Newtonian scale, and the Newtonian approximation is essentially perfect for that purpose. But something might shift, quietly, in how vast the world feels, in how strange and interesting the question of existence is when you really follow it, in how the ordinary, a cup of coffee, a face, a patch of morning light, becomes tinged with something deeper when you remember that it is happening in space-time, that it is a configuration of the dynamic fabric, that it is a moment in a structure that has no edges and no center, and extends in 4 dimensions through the whole of what exists. The ordinary does not become less real. It becomes more. There is one more chapter to visit before we return to stillness. One more facet of Einstein's secret that reveals just how alive, how dynamic, how genuinely physical the space-time fabric is. Gravitational waves. In 1916, 1 year after publishing General Relativity, Einstein predicted that accelerating masses should produce waves in space-time. Ripples propagating outward through the fabric, like the waves produced when a stone is dropped into water. He called them gravitational waves. But here's what he also believed for most of his life. These waves would be so unimaginably faint that they would never be detected. The energy needed to produce them was enormous. Events on the scale of colliding neutron stars or black holes. And, even then, by the time the ripples reached Earth from cosmic distances, the stretching and squeezing of space they caused would be incomprehensibly tiny. On the order of 1,000th the diameter of a proton, measured across a detector 4 kilometers long. No instrument could ever be that sensitive. Surely not. Even Einstein doubted they could ever be found. He was wrong. On September 14th, 2015, a century after Einstein first formulated general relativity, the 2 detectors of the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected a signal. It lasted 1/5 of a second. It was the signature of 2 black holes, one about 36 times the mass of the Sun, the other about 29 times. Spiraling together and merging into a single black hole roughly 1.3 billion light-years away. In those final fractions of a second before the merger, the 2 black holes were circling each other many times per second, generating gravitational waves that carried more power, momentarily, than all the light emitted by all the stars in the observable universe combined. And when those waves arrived at Earth, after traveling 1.3 billion years, LIGO's detectors felt them, felt space-time itself stretching and compressing by a distance smaller than any human technology had ever measured. The sound file synthesized from the data, the chirp as physicists call it, the rising tone as the 2 black holes spiraled inward faster and faster, is one of the most extraordinary things ever recorded. It is, in a very real sense, the sound of space-time. 2 massive objects wrapping space-time around themselves in a spiral, sending ripples across 1 billion light-years, arriving at a quiet detector in Louisiana and Washington state and saying, "We were here. We collided. We made a new black hole." And here on Earth, a century after the prediction, we heard it. Gravitational wave astronomy has since detected dozens more events. Neutron star mergers, black hole, collisions of various masses, each one a confirmation that space-time is not just a mathematical abstraction. It is a physical thing that can wave, that can ring, that can carry information across unimaginable distances. When 2 neutron stars merge, an event detected in 2017 and observed simultaneously in gravitational waves and light. The event produces a kilonova, an explosion rich in heavy elements: gold, platinum, uranium, the heavy elements that could not be produced in ordinary stellar nucleosynthesis. The atoms that make up these elements were forged in the extreme conditions of neutron star mergers and then scattered through space, eventually becoming part of new stellar systems, new planets. The gold in any ring you might be wearing was almost certainly produced in a neutron star merger billions of years ago. The ripples of that collision, in principle, spread outward through space-time. Every heavy element you carry is a memory of a space-time event. there is a thing that happens when you follow these ideas far enough. A kind of quiet vertigo, a sense of the ground shifting, not violently, but deeply. A realization that the world you thought you understood, the world that felt so solid and obvious and permanent, is built on something far stranger and more alive. Space-time is not a passive container. It is dynamic. It responds, it ripples, it curves. It carries the memory of every massive collision that has ever occurred in the form of waves spreading outward at the speed of light. The fabric of reality is not silent. It hums. Not with sound. There is no medium for sound in the vacuum of space, but with something analogous, with the geometric vibrations of the fabric itself, with the information of events that happened billions of years ago, still propagating, still spreading, still reaching new detectors, new observers, new ears capable of hearing them. And there's something else, something even quieter and perhaps even more profound. Those gravitational waves, those ripples in space-time, travel at the speed of light. They have been traveling for 1.3 billion years. And during all that time, they did not slow down. They did not dissipate in the way sound dissipates in air, or the way waves on water lose energy to friction. They spread and weakened through geometry, because the same amount of energy was spread over a larger and larger sphere as the wave expanded. But they did not lose energy to any medium. There was no medium to lose it to. Space-time itself is the medium, and space-time offers no resistance, no friction, no absorption. The ripples of that ancient black hole collision are still spreading right now. Long past Earth, through the outer solar system, through the interstellar medium, through the galaxy, outward, spreading forever, weakening with distance, but never stopping, never absorbed. There is a poetry in that. The universe remembers, in its fabric, every violent event that has ever occurred, not in a way we can access. The waves spread too thin too quickly, and our detectors can only find the strongest signals from the nearest events. But in principle, the fabric carries the imprint of everything. Every collision, every merger, every moment when mass accelerated violently enough to shake the geometry of space and time. The universe, in this sense, is self-documenting. The fabric of space-time is its own history. Before we move to the edge of what we know, let's spend a moment on something that is easy to overlook when you are absorbed in the ideas themselves. The extraordinary human story of how any of this came to be understood. Physics is often presented as a series of discoveries, as if the universe had a surface and humanity was slowly peeling it back to reveal the equations underneath. But this is not how it works. Physics is a conversation between human minds and physical reality, mediated by mathematics and experiment, accumulating over centuries, built on everything that came before. Einstein did not appear from nowhere. He stood on the shoulders of an enormous structure of prior thought. Galileo's understanding of relativity of motion, Newton's synthesis of mechanics and gravity, Faraday's intuition about fields, Maxwell's electrodynamics, Riemann's geometry of curved spaces, Lorentz's transformations, Poincaré's near glimpses. All of it was there, waiting, when Einstein arrived with the particular quality of mind needed to see the unified picture hiding inside. What made Einstein different, and this is worth spending a moment on, was not raw mathematical power. There were mathematicians of his generation who were more technically formidable. What Einstein had was an unusual capacity for what physicists sometimes call physical intuition. The ability to feel before proving what the mathematics must say. The ability to ask not, what does the equation produce, but What does the equation mean? It would take an idea, the constancy of the speed of light, say, and sit with it. Not rushing to calculate, not immediately reaching for equations, but asking quietly, patiently, if this is true, what must follow? If this is really true, what becomes impossible to maintain, and what must replace it? This quality of unhurried, rigorous imagination is what produced general relativity. The development of general relativity, in particular, took 10 years. From the publication of Special Relativity in 1905 to the final correct equations published in November 1915. 10 years of false starts, wrong turns, mathematical errors, conceptual breakthroughs, and the slow accumulation of understanding. At the beginning, Einstein knew the destination. Gravity had to be incorporated into a relativistic framework, had to be described in terms of curved spacetime. But the route was not clear. The mathematics he needed was not the mathematics he knew. He had to learn tensor calculus, differential geometry, the mathematics of curved spaces. He had to collaborate, to consult, to struggle. He made a major error in 1913 and was convinced for 2 years that the right equations could not be generally covariant, that they had to pick out a preferred reference frame. This turned out to be wrong, and realizing it was wrong required a difficult conceptual journey. In the final weeks of November 1915, working at extraordinary pace, he published a series of papers correcting his earlier work, and finally arrived at the field equations of general relativity in their correct form. One of the first things he did with the equations was calculate the precession of Mercury's orbit, the long-standing anomaly that no one had been able to explain. When the equations gave the right answer exactly without any adjustment, he was overwhelmed. He later described a state of palpitations and feeling as if he might have a heart attack from the excitement. This is not the story of a cold, calculating machine of a mind. This is the story of a person who was genuinely moved, genuinely shaken by the beauty of the correspondence between mathematics and reality. After 1915, the theory had to face the world. In 1919, a British astronomer named Arthur Eddington led expeditions to the island of Principe, off the coast of West Africa, and to Sobral in Brazil, to observe a total solar eclipse. The eclipse was crucial because it allowed the positions of stars near the sun's edge to be observed. Stars that would normally be hidden in the sun's glare. If Einstein was right, if the sun's gravity bent the fabric of space-time, and if light followed the curves of that fabric, then the apparent positions of these stars should be shifted slightly from their expected positions. The amount of shift was predicted precisely by general relativity, and it was different from what Newtonian gravity would predict. Eddington measured the positions of stars during the eclipse. The results confirmed Einstein. When the news broke, it became a sensation. Suddenly, the physicist from Bern, by 1919 a professor in Berlin, was famous. The equations that only a few dozen people in the world fully understood were described in newspaper headlines as overturning Newton and rewriting the fundamental laws of reality. Light all askew in the heavens, read one headline. Einstein theory triumphs, read another. The theory had passed the test. The universe had confirmed the prediction. Space-time curvature was not just elegant mathematics. It was physical reality. There is something deeply moving about the fact that it took a solar eclipse. That particular, precious, fleeting alignment of sun and moon, to make the test possible. That for a few minutes twice a year at most somewhere on Earth, the moon's disk perfectly occults the sun's disk and makes the stars near the solar edge visible in daylight. the universe provided the experiment, as if the cosmos, in its patient, indifferent way, had arranged this particular window of visibility, this particular configuration of orbital mechanics, and waited for a species clever enough to notice what it revealed. The margin of coincidence involved in total solar eclipses is itself extraordinary. The Sun is approximately 400 times the diameter of the Moon. It is also approximately 400 times farther away. These two facts combine to make the Sun and Moon appear almost exactly the same size in Earth's sky. Change either number appreciably and total solar eclipses either don't happen or don't block enough of the Sun's disk to reveal the corona and the nearby stars. This apparent coincidence, the result of the current geometry of the Earth-Moon-Sun system, which will not persist indefinitely as the Moon slowly drifts away, is one of the more extraordinary alignments in our cosmic neighborhood. And it was through this alignment that general relativity first spoke its confirmation to the world. The 100 years since have seen the theory tested in increasingly precise ways. Precise measurements of Mercury's precession confirmed at high accuracy. The gravitational deflection of light confirmed in many subsequent eclipse expeditions and eventually by radio astronomy and spacecraft tracking. Gravitational redshift, the slight decrease in the frequency of light climbing out of a gravitational well, confirmed in laboratory experiments as early as 1959, using gamma rays and the Nussbauer effect to measure the tiny frequency shift between a gamma ray source and detector separated by only 22 meters in height. The Pound-Rebka experiment, as it is known, confirmed that time runs slower at lower altitudes, slower at the floor of a building than at the top, not by much, a tiny fraction of a second per year, but measurably, repeatably, unambiguously. Gravitational lensing, the bending of light from distant galaxies by massive objects in the foreground, is now a standard tool of observational cosmology. Astronomers use it to detect the presence of dark matter, which bends light gravitationally even though it doesn't emit any, to map the distribution of mass in galaxy clusters, and even to magnify distant galaxies that would otherwise be too faint to study. The universe's own mass distribution acts as a gravitational lens. The predictions of general relativity are embedded in the tools of modern astronomy. The Hulse-Taylor binary pulsar, discovered in 1974, provided another astonishing test. A pulsar is a neutron star that emits a beam of radio waves from its magnetic pole. And if that beam sweeps across Earth as the neutron star rotates, we can detect it as a precise, regular pulse. Russell Hulse and Joseph Taylor discovered a pulsar with an unusual property. It was in a binary orbit with another neutron star. As the two neutron stars orbit each other, they should, according to general relativity, be emitting gravitational waves. And emitting gravitational waves means losing energy. And losing energy means the two stars should spiral slowly closer together. Their orbital period should decrease over time at a precise rate predicted by the theory. Hulse and Taylor measured the orbital period over years, decades, and it decreased at exactly the rate predicted by general relativity. This was the first indirect detection of gravitational waves. It won Hulse and Taylor the Nobel Prize in Physics in 1993. Einstein's theory tested again, confirmed again, at a precision that would have been unimaginable in 1915. And then, 40 years later, LIGO made the direct detection that we described earlier, the actual ripples in spacetime arriving at detectors on Earth after 1.3 billion years of travel. At the moment of the first detection, September 14th, 2015, at 5:51 a.m. Eastern Time, the LIGO detectors in Livingston, Louisiana, and Hanford, Washington, both registered the same signal, 7 milliseconds apart, the light travel time between them for the direction of the source. The signal matched perfectly the predicted waveform for a binary black hole merger. The scientists who had been working toward this moment for decades, who had spent careers building and refining instruments of extraordinary sensitivity, who had been through false alarms and funding battles and the long patience of experimental physics, were overwhelmed. One of the pioneers of LIGO, Kip Thorne, who had been working on the theoretical side of gravitational wave detection since the 1970s, had tears in his eyes. Physics had heard space-time speak. Kip Thorne is worth pausing on for a moment. He is the physicist, along with Rainer Weiss and Barry Barish, who won the Nobel Prize in Physics in 2017 for the detection of gravitational waves. He is one of the world's leading experts on general relativity. He has spent his career thinking about the most extreme conditions in the universe: black holes, neutron, stars, wormholes, the structure of space-time near singularities. And yet, he has also spent considerable energy thinking about how to communicate these ideas to people who are not physicists. He was involved in the scientific advising for the film Interstellar, helping Christopher Nolan's team understand what the environments near a black hole should look like, leading to a visual rendering of a black hole accretion disk that was not only aesthetically extraordinary, but scientifically accurate enough to generate a scientific paper. The image of the black hole gargantua in Interstellar, the swirling ring of light around a dark sphere, is not just a design choice. It is a simulation of what light would actually do in the extreme space-time curvature near a supermassive black hole. The way the upper and lower parts of the accretion disk appear to curve overhead is what gravitational lensing of the disk's own light should look like. The brightness differential between the approaching and receding sides of the disk is what Doppler shifting of relativistically moving gas should produce. The mathematics of general relativity, rendered as light on a screen. When science and art collaborate with this seriousness and this depth, something remarkable happens. Ideas that live in equations become visible. The geometry of space-time becomes, for a moment, something that can be seen and felt, not just calculated. We have come a long way. From the coffee cup on a morning table to the collision of black holes a billion light-years away. From the intuitive stability of everyday experience to the dynamic, observer-dependent, perpetually surprising structure that underlies it. But it would be dishonest, and in a way, it would do a disservice to the beauty of this whole story, to leave without acknowledging what we do not know. Because for all its extraordinary precision and predictive power, general relativity is not the final answer. It is an extraordinarily successful theory, confirmed to remarkable accuracy across an enormous range of scales and conditions. But it is not complete. There is another theory of comparable power and precision, quantum mechanics, and its successor, quantum field theory, that describes the behavior of matter and energy at the smallest scales. Particles, forces, the quantum vacuum, the framework from which our understanding of atoms, nuclei, and fundamental particles emerges. These two theories, general relativity and quantum mechanics, are the twin pillars of modern physics. And they disagree, not in ordinary circumstances, not at the scales where we normally apply them. General relativity is for the large, for gravity, for space-time, for black holes and galaxies. Quantum mechanics is for the small, for particles, for quantum fields, for atoms and molecules. Each is extraordinarily accurate in its domain, but there are situations involving both very high gravity and very small scales, where both theories must apply simultaneously. And in those situations, they give contradictory answers. The singularities inside black holes, the first instance after the Big Bang. Places where the curvature of space-time becomes extreme enough that quantum effects cannot be ignored. In those places, our current theories break down. They give infinities where there should be finite numbers. They lose predictive power. They fail. This is not a failure of the theories per se. It is a boundary, a signal that something new is needed. A deeper framework that reduces to general relativity in its domain and to quantum mechanics in its domain, but which goes beyond both when both apply simultaneously. This deeper framework does not yet exist. Not fully. There are candidates, string theory, loop quantum gravity, causal dynamical triangulation, and others. Some of these suggest that space-time itself, that smooth, continuous fabric we have been describing, may not be smooth and continuous at the very smallest scales. It may be discrete, granular, woven from something even more fundamental. The picture may be stranger still. Quantum mechanics on its own already suggests some extraordinary things about reality. The quantum world, the world of particles, of fields, of the phenomena described by quantum theory, is deeply strange in ways that even experts still argue about. Particles do not have definite positions or momenta until they are measured. Their properties are described by probability distributions, wave functions, that evolve in time and collapse, in some interpretation, upon observation. Particles can be entangled, their properties correlated over arbitrary distances in ways that cannot be explained by classical cause and effect. The very act of observation, of interaction, seems to affect what is observed, what any of this means for the nature of reality. Whether there is a single definite reality out there, independent of observation, or whether reality is in some sense participatory, or many-branched, or something else entirely, is one of the deepest and most contested questions in physics. And when you try to combine this strangeness with the dynamic, curved, observer-dependent space-time of general relativity, when you try to imagine a quantum theory of gravity, a theory of quantum space-time, the strangeness compounds. Some theories suggest that space and time may be emergent, not fundamental, that they arise from something deeper, the way temperature arises from the motion of molecules without being a property of any individual molecule, that the smooth, continuous space-time of general relativity is an approximation, valid at large scales, but fundamentally composed of something that has no spatial or temporal structure at the smallest scales. If this is right, and we do not yet know if it is, then the space-time fabric we have been describing is itself not the deepest layer. It is a description of a deeper something in a language that becomes available only at human-relevant scales. What is that deeper something? We do not know. We are genuinely at the edge, the frontier, the place where human understanding thins out and the unknown begins. This is not a cause for despair or frustration. It is, if anything, a cause for wonder. We live at a remarkable moment, a moment when enough of the universe has been understood that we can see the shape of our ignorance clearly, when we know enough to know what we do not know. When the questions that remain are the real ones, the deep ones, the ones that cannot be answered by patching old theories, but only by genuinely new thinking. The history of physics is a history of precisely this. Moments when old frameworks broke down under the pressure of new evidence, and something stranger and more beautiful emerged in their place. Newton breaking with Aristotle, Einstein breaking with Newton, quantum mechanics breaking with classical physics. Each transition was, at the time, deeply unsettling. Each required abandoning things that had seemed obvious, permanent, fixed. And each revealed a universe that was larger, stranger, more intricate, more astonishing than the previous picture had suggested. There is no reason to think we are at the end of this process. Every indication suggests we are not. The universe is not yet finished surprising us. We said earlier that the fundamental equations of physics are nearly time-symmetric, that they work equally well run forwards or backwards. Let's sit with that a little longer because it hides something important. If you filmed two billiard balls colliding and played the film backwards, you would see a perfectly valid physical event. The backwards version violates no laws. If you filmed the planets orbiting the sun and reversed it, the reversed version would look exactly as it should according to Newton and Einstein. But if you filmed a glass of milk being knocked off a table, the glass shattering, the milk spreading across the floor, and played it backwards, something would immediately feel wrong. You would know without thinking about it that you were watching a film in reverse. The scattered glass does not gather itself back into a glass. The milk does not flow upward and reconstitute itself into the intact vessel. Why? This is the question of the arrow of time, and it is one of the deepest questions in physics. The laws that govern the molecules of the glass and milk are time-symmetric. Individual molecular collisions are reversible. There is no law that says a broken glass cannot spontaneously reassemble. It is merely extraordinarily, almost incomprehensibly improbable. The reason is entropy. Entropy, loosely speaking, is a measure of how many different microscopic arrangements are consistent with a given macroscopic state. An intact glass sitting on a table has relatively few microscopic arrangements. All the molecules need to be in roughly the right positions and configurations to maintain the glass shape. A shattered glass spread across a floor has an enormous number of microscopic arrangements consistent with that scattered state. There are vastly more ways for things to be disordered than ordered. So when the molecules of a broken glass bounce around, exchanging energy, following perfectly time-symmetric laws, they almost certainly end up in one of the many disordered states, not one of the few ordered ones. The probability of them spontaneously reassembling the glass is not zero. It is just so small as to be effectively impossible on any human timescale. This is the second law of thermodynamics. Entropy tends to increase over time. Not because of any asymmetry in the fundamental laws, but because there are so many more high entropy states than low entropy ones. But here's the thing that makes this cosmological, rather than merely everyday. For entropy to increase, it has to start low. If the universe started in a state of high entropy, a disordered, maximally scrambled state, there would be no arrow of time. Things would just fluctuate randomly. The past and future would be statistically indistinguishable. The fact that we experience a clear arrow of time, that the past is fixed and the future is open, that broken glasses don't reassemble, that we remember yesterday and not tomorrow, means that the universe started in an extraordinarily low entropy state. The Big Bang was not just hot and dense. It was, in a very specific sense, extraordinarily ordered. Ordered in a way that has been driving entropy upward ever since. The second law of thermodynamics, the arrow of time, is ultimately a statement about the initial conditions of the universe. Why did the universe start in such a low entropy state? We don't fully know. This is called the past hypothesis in philosophy of physics, the assumption that the universe began in a special, low entropy condition. It is empirically well supported. The cosmic microwave background shows us the smooth, nearly uniform early universe, which is indeed a low entropy state. but a deep explanation for why it was low is still elusive. Some physicists speculate that this is a feature of whatever process created the universe. Perhaps quantum fluctuations in some pre-Big Bang state, perhaps some deeper cosmological principle, perhaps something entirely new. The question is open. What does this have to do with space-time? Everything. Remember that in the block universe view, in the four-dimensional space-time picture, the past and future are both real. Both are there in the block. The distinction between them is not a feature of the fundamental equations. It is a feature of the distribution of matter and energy within the block. Specifically, the fact that entropy increases in one direction along the time axis. The arrow of time is not written into space-time itself. It is written into the history of the universe that space-time contains. In a universe with different initial conditions, a high entropy beginning, there might be no arrow of time. No clear sense of past and future, no memory, no causation in the familiar sense. The particular shape of our cosmos, the story of increasing entropy from a low entropy beginning, is what gives time its direction. What makes the future different from the past? What makes you remember yesterday and not tomorrow? Your experience of time flowing in one direction is a consequence of cosmology, of the particular history your universe has had. Another universe, beginning differently, might have no equivalent experience. There's something in this that cuts very close to questions of consciousness and experience. Memory requires a direction of time. Causation requires a direction of time. Learning, growth, narrative, the things that make a life feel like a life, all require the past to be different from the future in a specific way. The past is fixed and remembered. The future is open and anticipated. This asymmetry, which physics tells us is ultimately cosmological, a feature of entropy, is what makes experience possible. The felt sense of time passing, of one moment following another, of story and meaning accumulating. All of this is downstream of the second law of thermodynamics, which is downstream of the initial conditions of the universe, which is ultimately a fact about the particular block of space-time that we happen to inhabit. This is not a cold or reductive observation. It does not make memory less precious or narrative less meaningful. If anything, it makes them more astonishing. That the universe should have started in just such a way as to produce the conditions for experience, for beings who can remember and anticipate and make meaning, is not something we can fully explain or fully take for granted. It is simply the case. And it is, like so much else in this story, strange and beautiful. One final thought before we move toward the edge of what is known. We tend to think of our experience of time as a passive reception, as if time is a river and we are floating in it, carried along by forces outside ourselves. But there is another way to think about it. You are a physical process. You are a complex, dynamic arrangement of matter and energy, processing information, storing patterns, updating models of the world in real time. The experience of now, the felt sense of the present moment, is not just something that happens to you. It is something you are doing. Your nervous system is constantly processing incoming information, integrating it with stored patterns, predicting the near future, updating the model of the present. This processing takes time, fractions of a second. The now you experience is not the instantaneous present, but a brief window of processed information stitched together by your brain into a seamless felt experience. Neuroscientists sometimes say we live in the past by a few hundred milliseconds. The time it takes for neural processing to construct the conscious moment. The present, as you experience it, is, in a very real sense, a construction, a model. A story your brain tells you about what is happening, assembled from physical inputs and biological processes, and the particular space-time path your body is tracing. And that construction, that remarkable, intimate, continuous, never-repeating construction, is your life. Not a reflection of reality, a participation in it, a mode of being inside it. Physics, at its deepest, leads not to a cold world of equations, but to a world that is strange and intimate simultaneously. A world in which the very things that feel most personal, the present moment, the flow of time, the sense of being here, are grounded in the large-scale physics of the cosmos, in entropy and expansion and initial conditions and the geometry of a four-dimensional fabric. The personal and the cosmic are not separate. They are the same thing, seen from different scales. You are not a small being in a large universe. You are the universe at one particular scale, experiencing itself from the inside. Before we return, one last image. There's a photograph taken by the Voyager 1 spacecraft on February 14th, 1990. At the request of the astronomer Carl Sagan, the spacecraft turned its camera back toward the Sun from a distance of about 6 billion kilometers, far out in the solar system, beyond Neptune. It took a series of photographs. In one of them, among scattered bands of light caused by lens flare from the Sun nearby, there is a tiny point, a pale blue dot, almost invisible, barely worth noticing against the expanse of darkness surrounding it. That is Earth. Every human being who has ever lived, every war, every love story, every act of cruelty and kindness, every piece of music ever written, every child ever born, every city, every ocean, every mountain, all of it suspended on that point of light. Sagan wrote about this photograph, and what he said is worth returning to here in the context of everything we have discussed. He wrote that the photograph underscores our responsibility to deal more kindly with one another and to preserve and cherish that pale blue dot, the only home we have ever known. What we can add from the physics is this: that pale blue dot exists in space-time. It is not a fixed point in an absolute space. It is a location in a four-dimensional fabric that has been stretching and curving and rippling for nearly 14 billion years. The atoms that make up every person on that dot were forged in stellar interiors across billions of years of cosmic history. The planet itself formed from the remnants of earlier stars whose gravitational waves very faintly still spread outward through the galaxy. The ordinary-seeming world has extraordinary depths, and we are part of it. Not just in it, part of it. This is what Einstein's space-time secret ultimately gives us, if we let it. Not just a more accurate model of gravity, not just better GPS, but a different sense of what we are and where we are, and how deeply the large-scale physics of the cosmos is woven through the fabric of even the most everyday experience. The coffee cup on the table, the morning light, the slow passage of an afternoon, all of it in space-time, all of it subject to its geometry, all of it real and strange and worth noticing. And now, quietly, let's come back. Back to you. Back to here. Back to this moment that is, despite everything we have explored, still genuinely yours. You have traveled a long way in these pages through ideas that press at the edges of what human intuition can comfortably hold. You have visited the inside of thought experiments where clocks run slow and light behaves impossibly. You have zoomed out to galaxies and black holes and the fabric of space-time stretching across the observable universe. You have touched the edge of what physics knows and peered briefly into the vast territory of what it does not yet. And now it's time to come home. Not because the journey was too much, but because the destination was always here. Sit for a moment with what you know. You know that time is passing. You feel it, even now. The quiet accumulation of moments, the strange steadiness of experience moving forward in one direction, carrying everything with it. You know that the ground beneath your feet, the planet you are sitting on, is a massive object curving space-time around it. You know that this curvature makes clocks at your feet tick very slightly slower than clocks at your head. You know that you are, even now, in freefall around the sun, following a geodesic through curved space-time, tracing a path determined not by invisible forces, but by the shape of the fabric itself. You know that the light coming through your window, whether it's daylight or street light or screen glow, has traveled at 300,000 kilometers per second to reach you, and that this speed is the same for every observer in the universe, regardless of their motion. You know that the stars you might see tonight, if you look up, are showing you the past. Some of them showing you hundreds of years ago, some of them thousands, some of them in galaxies beyond our own, millions or billions. You know that somewhere in the darkness between those points of light, gravitational waves are spreading outward from events that happened before life existed on Earth. The fabric carrying information about collisions and mergers and the violent rearrangements of matter on cosmic scales. You know that your now, this specific, intimate, undeniable present moment, is yours. Unique to your position in space-time, not shared in the absolute sense with anyone else, though close enough to shared for all practical purposes of human life. What does it feel like to hold all of this and still be here? Still be in this body, in this place, in this moment that is. Despite its cosmic impermanence, despite its tiny scale in the face of all that exists. Real? Quietly? Completely real? There's something that can happen when you really absorb the scale and strangeness of the universe. Not as a list of facts, but as a felt reality. It can produce awe, certainly. That particular kind of expanded chest feeling, that sense of the self momentarily stepping back from the small concerns of daily life and glimpsing something genuinely vast. But it can also produce something quieter, a kind of tenderness, a gentle recognition that this moment, this specific, ordinary, unrepeatable moment of being here and aware and alive, is embedded in something extraordinary, not in spite of the physics, because of it. Because if space and time are a single fabric, and that fabric curves and ripples and responds to everything within it, then this moment is not taking place against a neutral backdrop. It is happening within something, within a dynamic, responsive, ancient, extraordinary structure that extends without limit in all directions, that contains the histories of 1 trillion galaxies, that hums with the remnants of a Big Bang nearly 14 billion years ago. You are not separate from that structure, you are part of it. Your body, every atom in it, was forged in stars, scattered through space, assembled slowly through billions of years of chemistry and biology. You are, in the most literal sense, the universe folded back on itself, arranged into a form capable of asking questions about where it came from and what it is. The space-time fabric that contains you was shaped, in tiny part, by the mass of your body. You are not a passenger in the universe. You are a feature of it, a configuration of it, a momentary, complex, self-aware expression of the same fabric that stretches from here to the edge of the observable cosmos. Einstein knew this in his way. He was not a religious man in any traditional sense, but he spoke often of what he called cosmic religious feeling, a sense of the deep order and beauty underlying the universe, a humility before the mystery of existence, an awe at the intelligibility of the cosmos. "The most beautiful thing we can experience is the mysterious," he wrote once. "It is the source of all true art and science. He to whom this emotion is a stranger, who can no longer pause to wonder and stand wrapped in awe, is as good as dead. His eyes are closed." He was not asking us to believe in anything in particular, not to join any tradition or subscribe to any creed. He was simply pointing to something he had found in the mathematics, in the physics, in the long, careful work of following the universe wherever it led. That the universe is beautiful, that it is ordered, that it is, in some sense, not easily articulated, coherent, deeply, intrinsically, surprisingly, coherent in a way that none of the premises of science required it to be. That the laws that govern the motion of planets also govern the behavior of atoms. That the equations that describe gravity's hold on galaxies also describe the slight drift of a GPS satellite. That the same framework, the same elegant four-dimensional geometry of spacetime, unites the billion-year arc of cosmic history with the nanosecond precision of modern technology. This coherence is not something physics can fully explain. It is something physics reveals. And in revealing it, it invites a kind of wonder that is not about having all the answers, but about genuinely feeling the weight of the questions. There is a kind of knowledge that works on you slowly. Not the first time you hear it, not the second time, but somewhere after many encounters. When you have turned the idea over and over and let it become familiar without becoming ordinary, something changes. The idea stops being information and starts being perspective. It starts coloring everything else. It becomes part of how you see. The ideas we have explored in this film are like that. You will probably not walk away from this changed in any obvious sense. You will still need breakfast and sleep and human connection. You will still feel time passing at its ordinary felt rate. You will still experience your present moment as vivid and unique and undeniably now. But maybe, just maybe, some residue of this will stay. Not as a set of remembered facts, though the facts are real and important, but as a felt sense of the strangeness and depth of the world. A quiet awareness that underneath the familiar surface of things, something extraordinary is happening all the time. Space-time is not a background, it is an active participant. It curves and ripples around everything. It connects every moment to every other moment through the geometry of a four-dimensional fabric. It is older than anything it contains, and it will outlast everything that exists within it. And you are in it, right now. Take a moment. If there is a window near you, look out of it. The light reaching your eyes, whether it is sunlight or moonlight or streetlight or the dim glow of an overcast sky, has traveled at 300,000 kilometers per second to be here. The photons striking your retina were launched from their sources moments ago. Or, in the case of sunlight, 8 minutes ago from the surface of the sun. The ground beneath you is a massive object, bending space-time. You are in its gravitational well. Your clocks, including the biological clocks of your cells, the rhythms of your heartbeat and your breath, are running at a slightly different rate than they would if you were farther from Earth's center. The air around you is full of particles that were created in stellar interiors and scattered through space in stellar winds and supernovae, eventually finding their way into the molecular cloud that became our solar system, the planet that formed from it, the chemistry that produced the atmosphere you are breathing. Every breath is a cosmic event. Every moment is space-time. We began this film with the observation that time feels constant and space feels fixed, that the world of everyday experience is stable, predictable, intuitive. And it is, at our scale. The Newtonian approximation is genuinely excellent for human-scale life, but underneath it, wrapped inside it, making it possible, is a deeper structure, a stranger one. One that turns out to be far more dynamic, far more relational, far more extraordinary than the obvious surface suggests. That's the secret Einstein uncovered, not in a single dramatic moment, not with a shout, but with the quiet, sustained attention of a mind, willing to follow the logic wherever it led. Even when it led somewhere that common sense resisted, even when it meant letting go of assumptions so deep they didn't feel like assumptions at all. Space and time are not separate. They are space-time. Space-time is not fixed. It is dynamic. It curves, it stretches, it ripples, it responds. Time is not universal. It flows at different rates in different conditions. The present moment is not shared. Each observer has their own now. And perhaps, though this is not certain and is still being explored, the past and the future are as real as the present. The block of space-time laid out in 4 dimensions, containing all events, all moments, all of what has been and what will be. These are not just ideas, they are the shape of reality. We close softly the way a long walk ends, not abruptly, but with a gradual slowing, a quieting, a return. The universe is patient. It has been here for nearly 14 billion years, and it will continue long after the last star has burned out and the last black hole has evaporated in a whisper of Hawking radiation. It does not need our understanding. It does not depend on being observed to be real. And yet it can be understood. That is the astonishing thing. That is the thing that should, perhaps, give us the deepest pause. We are creatures that evolved on a small planet around a medium star in an ordinary galaxy, and we have managed, through curiosity and mathematics and the willingness to be surprised, to understand something of the deep structure of the thing we live in. That is not nothing. That is quietly everything. Thank you for being here with us on Infinite Science. Not in a hurried way, not rushing forward to the next thing, but here for a while in this unusual company of ideas that press at the edges of what can be fully imagined, and a universe that is always, quietly, stranger than we expect. The questions are not finished. They never are. There are things we do not know, deep things, things that will require new mathematics and new observations and new ways of thinking. The frontier is real, and the unknown beyond it is vast. But this is, we think, a good place to rest for a moment. To sit with the space-time fabric wrapped around you, with the light crossing vast distances to reach your eyes, with the gentle passage of your own personal now, through the 4-dimensional structure of what exists. And to wonder, quietly, without urgency, with the particular patience that the universe itself seems to model. Endlessly patient, endlessly complex, endlessly willing to surprise. Maybe reality is exactly as strange as the mathematics suggests. Maybe time is exactly as personal and as relational and as extraordinary as Einstein described. Maybe the past is not gone and the future is not entirely absent, but both are there in the structure of space-time, exactly as real as this moment, which is also, whatever now ultimately means, exactly, undeniably, beautifully real. And maybe the universe is far stranger and more beautiful than we ever imagined. Until next time, from all of us here at Infinite Science, take care of yourselves, look up sometimes, and stay curious.